So the sounds we heard from the singing bowl or from a guitar string or even the sound coming out of our mouths are complex combinations of sine waves that form a rich sound that we perceive to be a certain kind of a thing, a trombone, a violin, somebody's voice. If we even take a simple sine wave, it turns out we can't really represent that continuously on a computer. What we can do is we can sample the sine wave and approximate it by sending along those samples to the sound card of a computer, and it would then reproduce the sound coming out of a speaker. So let's take a look at a couple examples of this. A good analogy would be if you've taken a picture on your cell phone or on a camera at relatively low resolution, you might be able to make out the landscape or the person's face that you see, but it's going to be lacking some detail. As you increase the resolution, it gets sharper and sharper. At the highest resolution on the devices we use now, even though the samples that are taken are discrete, they're so close to each other that the image looks very real. The same thing is going to be true of sound. If we sample the sound often enough, we'll get such a good approximation to the continuous sine wave that our ears will not be able to hear the difference. So let's take a look at a sine wave that was sampled about 5,000 times a second, as shown here. Because we know it's a sine wave, we pretty much interpolate using our eyes the spaces that are not actually represented by dots. And we can see that it is a sine wave. But as we increase the resolution to about 11,000, 22,000, and finally 44,100 samples per second, the sine wave becomes clearer and clearer as more points are represented. Now it turns out that 44,100 is a common number in the sound industry because it's exactly the rate at which an electronic or digitized song is expected to be played on an electronic device. So the sound card on your computer reproduces high-definition sound based on it getting samples at the rate of 44,100 per second. How do we produce such a sound using a program? Here we see a sine wave with the approximations again shown in gray of the samplings. If we have a sound wave, a sine wave, that's oscillating at a given hertz, say 440 hertz, we can think about each cycle taking 2 pi radians. Then we're going to oscillate h times per second if it's h hertz. With the frequency of that speed, suppose it's 440 hertz, we need to take samples so that 1 second takes up exactly 44,100 samples. So let's take a look at how we would write code to do this. We would need to take the sine function of 2 pi radians times h, if that's our frequency in hertz. That's basically a continuous representation of a sine wave that oscillates at the given frequency. But we have to sample it. Imagine that I is going to go from 0 to 44,100, covering the span of a second. By taking each of these values and multiplying by I divided by 44,100, we crawl along the sine wave for 1 second's worth of time, and in doing so, we compute the value of the sine function at each of those intermediate points. So the code that we see here works by sampling a sound wave. The hertz variable is set to 440, but we can set it to any frequency we want. 440 corresponds to pitch 0 in our encoding, or concert A. 880 would be an octave above that. Suppose we wish the sine wave to play for exactly 1.5 seconds, and our sample rate, as said before, is 44,100 samples per second. How many total samples do we need? Well, if this is going to last 1.5 seconds, we need 44,100 plus half again as much. So we take the number of seconds, 1.5, multiply by our sample rate to get the total number of samples we're going to send to the sound card. So the sound card is expecting those samples to come at 44,100 per second, so it will reconstruct the sine wave based on that contractual agreement and play for exactly 1.5 seconds. We then provision an array A, which has enough space to hold all of these samples. It's going to be double values. These values go between 0 generally and 1, and 0 and -1, so we need doubles to be able to represent their values. The for loop then goes over the range of the samples we need to compute, each time computing for each index I the sine function of 2 pi times the frequency in hertz, then multiplied by I, the sample number, divided by the sample rate. So for 1.5 seconds, this function is going to basically do 44,000 samples plus half again as much to play for 1.5 seconds. Once those samples are complete and stored into the array A, we then provide that to the sound card by saying standard audio.play, and the sound card will reproduce concert A for 1.5 seconds. In terms of an animation of how this proceeds, imagine that A0 is our first sample, with I being 0, the sign's argument is going to be 0, 2 pi times 0, and that the sine function of 0 is exactly 0. And as we crawl a little bit along the curve, suppose I becomes 1, we also crawl correspondingly up the sine function slightly to the next sample point, shown where the gray area intersects the red curve. We store that value in A of 1, we crawl a little bit further to the right, and store that value into A of 2, and so on. After we've sampled this sine wave enough times, namely the number of seconds times the sample rate, those values are stored in the array, and we then play the array through the sound card.